Okay, so welcome to this module of thermochemistry. So, thermochemistry deals with the study of heat transfer in chemical reactions. Heat transfer at a constant pressure is called change in enthalpy, that we already know, and we have already defined that earlier. So, therefore, in order to calculate the change in enthalpy, we need to calculate the process in constant pressure. Temperature is not required to be, like, temperature can be anything, we can define any particular temperature for that, it is not important to be a particular value. Now, since it is a enthalpy change, we have to talk about a reference state with respect to which we will calculate the change, and that is called reference state. And typically when we calculate the change in enthalpy, we calculate from something called standard states, and then that gives us standard enthalpy, and that at a 1 bar pressure and at any specified temperature. So, what is the standard state? Standard state of a system is its pure form at 1 bar pressure at a specified temperature. So, for example, nitrogen at 298 Kelvin at 1 bar pressure will be in gaseous form, carbon will at the same temperature at 1 bar pressure will be in graphite in a solid form, mercury will be in liquid form, water will be in liquid form, hydrogen will be in gas form. So, those are standard state at 1 bar pressure at a specified temperature. However, water will not be liquid at a very high temperature, right. In that, let us say 373 Kelvin, 378 Kelvin, let us say. At 378 Kelvin at 1 bar pressure, water will be in vapor form. So, that those things we have to consider, that what is the most stable form at a specified temperature at 1 bar pressure, and with respect to that we are going to calculate the change in enthalpy, which will give us the heat of formations, which will give us this enthalpy change, and that is what thermochemistry is all about. So, and when you calculate this enthalpy change, we always use the standard state, so that we get standard enthalpy change. So, standard enthalpy change is denoted as delta H with this particular sign, which by definition is the enthalpy difference for a process where initial and final substances are in their standard states. So, that automatically means that standard enthalpy for formation of an element in their reference state is 0, because that is the reference point from where we are starting. So, nitrogen, formation of a nitrogen gas at 1 bar pressure will be 0, because that is the reference state. So, here we already discussed about exothermic and endothermic reactions, but here we are going to specify once more. So, look at this particular profile, enthalpy profile, y axis is enthalpy and x axis will be the reaction coordinate, and this particular process reactant is getting converted to product and the enthalpy is becoming lower. So, in this process the delta H is negative, which means that same amount of heat is going to be released. So, because the heat is getting released in this particular process, we call that as exothermic reaction. In this particular process, again this much amount of heat needs to be supplied for the reaction to happen, delta H is positive and heat is going to be taken in by the system. This is called endothermic reactions. Hi, welcome to chemistry department of IISER Pune. We are right now in the 3rd floor of the chemistry wing. I am going to take you to one of the organic chemistry lab, where you can see the wonderful instruments that they use in order to carry out their research work. However, we are going to use very simple instrument and simple experiment in order to demonstrate exothermic and endothermic reactions. Okay, so in the class I have discussed about the exothermic and endothermic reactions. Now, we are going to demonstrate exothermic and endothermic processes in this particular lab, and you see this is an organic chemistry lab, and you can see there are a lot of equipments and other things are there. However, we are not going to use such a complicated thing. In order to demonstrate the exothermic reactions, we are going to use sodium hydroxide beads, as you can see here. Each they are called pellets, sodium hydroxide pellets, and normal water. So, you know what happens in an exothermic reaction, that when two things mix together, then it goes to a more stable state and releases heat. Now, you can understand the release of heat by measuring the temperature. First, what you are going to do is that we are going to demonstrate you the experiment. So, I will first pour water in a beaker and measure the temperature. So, as you can see,
the temperature of the water is 25 degree centigrade currently. Now, I am going to drop some sodium hydroxide pellets in the water, and you will see that the heat is going to be released, because sodium hydroxide and water will form solutions of sodium hydroxide in water. I will drop all of them actually, and they are going to react and they are going to go to more stable state, and therefore, they are going to release heat, and that heat we can measure by using temperature. So, I am going to start it now just to make the process a little bit faster, otherwise also it will dissolve after some time. Now, you see it is almost becoming a saturated sodium hydroxide solution, and I can see the temperature is increasing a little bit, but I will start a little bit more just to dissolve it. And you can see the temperature has already become 41 degree centigrade. So, just to tell you, the temperature of this particular room is, however, normal 25 degree centigrade or 24 degree centigrade, and that, as we have demonstrated in zeroth law of thermodynamics, that everywhere the air touches the surface will have the similar temperature. I can show you that. As you can see, it is 24.4 degree, and let us measure the temperature of the wall. As you can see, it is 23.9 degree, and any surface that we can think of. For example, I measure the temperature of the floor, see 24.1 degree, and now when I go back to the solution, hopefully the temperature has increased even further. No, so temperature is 38.4 degree. Yeah, so now since it is dissolved, now what is going to happen is that slowly the temperature will come down to the normal room temperature, because it is an exothermic reaction. So, heat is being released to the environment, and thereby the initial temperature that we saw, or initial heat that we saw by measuring the temperature, is going to get lower and lower, and the temperature is going to go to equilibrate to normal room temperature. Now, we are going to show an example of an endothermic reaction, and for that what we are going to use is ammonium chloride. As you can see here, we have taken already some ammonium chloride on the piece of paper, and this is just plain water. Remember, last time when you put sodium hydroxide, the temperature increased. Now, in this particular case the temperature should decrease. So, we will measure the temperature first of the normal water, and you can see the temperature is 23.3. Now, we are going to add ammonium chloride, okay, I am going to put all of that, and we will start it a bit. Yeah, I can feel the temperature decrease already. Just to show you, the temperature of ammonium chloride itself is actually 24 degree. However, when you do that for the water, and you can see it has already come down to 12 degree. So, when it will be dissolved a little bit more, the temperature will decrease further. As you can see, the temperature is 10.9 degree. And further studying, temperature is still decreasing. However, after some time, what will happen is that the temperature will equilibrate to the normal temperature of the room, and it will come to the equilibrium with the surrounding. But right now, in the beginning of this reaction, as the reaction is progressing, the temperature is getting down, and that is an example of an endothermic reaction.
So, in our body there are a lot of reactions always happening, and there are proteins and DNA which are biomolecules which do carry out a lot of different functions. We are showing a particular structure of a protein which normally in the folded state is functional and in the unfolded state is not functional, and this folding unfolding process keep on happening in our body, and those processes will essentially involve a change in enthalpy. Similarly, proteins bind the DNA and carry out lot of functions, and there also the same thing will happen. So, here there is an example where we are showing that binding of a protein to the DNA we are showing as an enthalpically favorable process. However, it need not be, we are just giving one example. Similarly, we are showing an unfolding of protein as an enthalpically forbidden process, or not forbidden, but enthalpically costly process. Delta H is negative positive, which means we have to put that heat in to the system. It may or may not be the case, it is just a prototype example. So, the point is to show that even for this kind of conformational changes, there will be a change associated with the enthalpy. Same is true for formation of a dimer from monomer, and again it is shown as enthalpically favorable process. So, in the macroscopic level there are many different changes happen. One can categorize that those changes as enthalpy of transition, and you see the transition is written as delta TRS H with that sign. So, earlier notation was it was delta H TRS, but since we are talking about a particular type of change, therefore, the notation is current notation is associated with the delta itself. So, physical changes can be of different types, such as vaporization, fusion, sublimation, all those are physical changes, where there is no such chemical reaction is happening. Water is going from ice to water, there is no chemical reactions going, it is just that the phase is changing from one form to another form. Just like we know in conformation, one conformation is changing from one conformation to another one, there also an enthalpy as change is associated with that. Here also the same thing, enthalpy change is associated with that. Second type would be enthalpy of formation, denoted as delta F, formation of CO2 from carbon and oxygen. So, carbon is in the solid state, oxygen will be in the gaseous state and forming a CO2 in the gaseous state. This will be a reaction, and this is basically if we calculate this reaction enthalpy, we are going to get heat of formation of CO2. So, essentially there is no difference between all the different forms, but we have to only look at the process that is happening. Standard enthalpy of a reaction is when we calculate the total change in the enthalpy of formation of all the products minus enthalpy of formation of all the reactants multiplied by the stoichiometric ratios. For example, in this reaction 2A plus B going to 3C plus D, we are going to calculate the total change in the standard enthalpy of reaction as 3 multiplied by formation of C, 1 multiplied by formation of D, and subtract it from 2 multiplied by heat of formation of A and 1 multiplied by heat of formation of B. So, and we can in general we can of course write down the whole process as this one nu j is the coefficient, and then heat of formation, standard heat of formation of all the components, where we have to know that nu j's are negative for reactants, and this will give us the reaction enthalpy, standard reaction enthalpy, and the notation is slightly different. It is this, the notation is this basically. Okay. And here you see several different other types of transitions are mentioned. For example, there is a phase transition from alpha to beta, we can call that as transition enthalpy. Then there is a fusion, which is going from solid to liquid, vaporization, liquid to gas, sublimation, solid to gas, mixing, then solution. For example, you put some sugar in water, it will be dissolved. So, there will be an enthalpy change associated with that as well. So, we and for the protein and other things we showed binding enthalpies, we showed conformational enthalpies, those are also there. So, any process that you can think of, for example, hydration, something is going from gas state to aqueous state, sodium hydroxide, let us say going from solid state to aqueous state. Atomization, ionization, electron gain, reactions, combustions, formations, so all different processes can have their own enthalpy changes, and whenever we consider an overall change, we will have to see what kind of processes are happening and add them together to get the total change of the enthalpy. Now, we can do that. I said that we have to add up, right. I said that in a hurry. We can do that because enthalpy is a state function. That is why when it goes from A to B to C, we do not have to care how it is going. We just have to calculate the difference between B and A, and we will get a value, and then C and B, and we will get a value, and we will add them together because it is a state function. So, enthalpy is a state function. So, one can combine two different processes such as fusion and vaporization, let us say, to get the overall change for solid to vapor. We know solid to liquid, we know, let us say we know liquid to gas, which is vaporization, we know solid to liquid, which is melting, and solid to liquid is melting, and opposite process is fusion, right. And then we can add them together here. So, let us say you can add these two processes and we can get the combined process for sublimation. And Hess's law says that is in very similar terms that you can do even for not for phase change, you can do that for reactions as well. You can combine one or more reactions to get an overall change in the initial and final reactions, and we are going to use that a lot in order to calculate the enthalpy in different processes and reactions. And also it is reversible because again it is a state function, it does not matter. So, for example, here we are talking about solid to liquid as 6.01 kilojoule per mole, right. Similarly, liquid to solid will be minus 6.01 kilojoule per mole. So, solid to liquid you can say that is melting. Similarly, liquid to solid will be fusion, it will be just the negative of that, and that we can do again because it is a state function. Now, we are going to give you an example. So, we are going to talk about heat of formation of CO2. So, what are the components involved in that? So, see the standard state of the carbon is graphite, which is a solid, and standard state of oxygen is gas. So, you have to start from there because they are 0, right. So, that is here you see, but in order to form CO2, we need to have the oxygen from O2 molecule to oxygen atom. So, you have to break the bond, and that cost energy. How much? So, you can see that going from O2 gas to O, it cost 498.34 kilojoule per mole. Again, carbon also need to be need to go from solid state to gaseous state, right, and that requires 716.68. So, these are endothermic processes because we have to supply enthalpy, but then once we get these two things, we can add them together and it will form CO2, which however is an exothermic process, because where does this form actually, why it is an exothermic process? Due to the bond formation, it becomes more stabilized, and therefore, the heat will be released. And how much is that? You can see that now if you start from that state like this state, it comes all the way here, which is 1215.02 minus 393.51. This is the total amount of bonding energy that we get by making C and O. And how did I calculate that? Because I know from this is 0 and this is a positive 1215.02 and this is my negative 393.51, right. So, I am now taking a difference from here to here, therefore, it will be 393 minus this one. and that is how we get this total number, right. We can calculate that. I do not know whether I did it right or not, but this is like I just summed both this. Okay. So, this is how we get the heat of formation of. So, remember where our 0 is, that is very important. We need to know that 0 heat of formation of CO2, because we are going to start from the standard state of C, standard state of oxygen and standard state of CO2. Therefore, this is our 0. So, since this is our 0, so heat of formation is only this much. Sorry, this is the only heat of formation is minus 393.51. However, the bonding energy that we get between gaseous carbon and gaseous atomic oxygen is this much, because this is a 0. So, standard state of carbon and oxygen we are getting this much stabilization. So, that is the heat of formation minus 393.51, that is not a problem, but we have to supply energy to go to this state, you have to supply energy to go to this state, and that is a positive value to, and bonding overcomes that positive value and comes to negative. So, the bonding has to be stronger than even the energy required or enthalpy required to sublime the or put the carbon in the gaseous state and oxygen and making oxygen atomic. Okay. So, I guess that is clear. Now combining various enthalpy of formations is possible. So, for example, these are different formation enthalpies for water minus 285.83. So, we remember we are discussing about which is more stable, methane or water, right. We can get that from heat of formation. So, water's heat of formation is minus 285.83 and methane's is approximately minus 74, and we know that if we burn methane we will get carbon dioxide and water, right, both of which are more stable than methane. So, that is where we can actually understand which is having higher internal energy and which is having lower internal energy. So, we can see water in the gaseous state also and then different things. So, we are going to only talk about the formation of KCl, what are the things involved in formation of KCl. So, for KCl again we start from, this is our 0 state where potassium is a solid and chlorine is a gas in Cl2. So, in order to make it from potassium solid to gas, you need to supply plus 89, and then in order to break the bond in chlorine you need to supply plus 122, and then there is an electron transfer that has to happen between chlorine and potassium, right, that becomes K plus and Cl minus, and that is again an enthalpically endothermic process, you have to supply that. Once you form that, then so that just to just take out the electron from potassium. However, when the chlorine takes in the electron, so what is that called, right, when you take out electron from an atom? Ionization energy. So, this is the typical ionization energy that is required, and then this thing will form where potassium, and so that is the stabilization, that is called when it will take the chlorine will take the electron affinity. So, because chlorine has higher electron affinity, so it will become there, and then finally you are getting the interactions due to ionic interactions between the K plus and Cl minus forming this thing. So, if I ask you how much is the formation, heat of formation for potassium chloride, what will be the value? It is only this much, okay, because we started from there and we ended up here. But if I ask you that, okay, what is the interaction enthalpy between potassium ion and chloride ion, then it is this much, okay. So, by writing them along the enthalpy axis, you will be able to figure out all possible contributions to overall change in the enthalpy. And remember, enthalpy and internal energy are very similar, except there is a difference. One is internal energy is heat at a constant volume and enthalpy is heat at a constant pressure, and between them there is just work done PV, and that is actually very small. So, often from heat of heat of formation we can understand the internal energy of the system. Okay. Okay, so, now that is being done, there is a problem here. So, the title is not correct, but we were just one a tutorial problem, let us say. Example. So, what he says that how many meters of stairway could a 70 kg man climb with a slope of 30 degree if all the energy available in metabolizing 18 gram spoonful of 18 gram glucose to CO2 and H2O could be converted to work. So, what it is saying is that, so glucose is C6H12O6 and it requires some oxygen to form CO2 and H2O. So, that is the combustion of glucose or metabolization of glucose. Let us say everything is converted to energy. How much energy it will give us? Since it is a heat of reaction, we can get the heat of reaction from balancing the equation. So, we have to balance the equation first. So, we can say 6 CO2. So, it will gives us 12 oxygen and we have 6 oxygen here. So, that will give us that, but we need 6 H2O in order to get 12 hydrogen. We got that, and now how many oxygens? So, 12 plus 6 18 oxygen, we have only 6. So, we need 12. So, this will be 6. Okay. So, now this reaction is balanced. Now, in order to get the enthalpy of this reaction, we need to have enthalpy of formation of CO2 multiplied by 6 plus enthalpy of formation of H2O multiplied by 6 minus enthalpy of formation of C6H12O6 minus 6 into enthalpy of formation of O2, correct. Now, we have got the values here, minus 393.5 into 6 minus 283.5 into 6 minus is plus now 1275, and what is the enthalpy of oxygen? 0, good. So, that will be 0. So, can you tell me the value here? Just calculate that and tell me. So, I can also do that. I do not want to do any mistake here. So, I am getting this value, correct. So, this is the kilojoule per mole that is energy available to us, right. Now, let us see that how much we can climb with that. So, I am going to delete everything else, remember 2787. So, it is a good point. So, we are getting minus 2787 kilojoule per mole of energy or enthalpy, let us say. So, that is for one particular mole. Now, we are using how much sugar? We are using 18 gram of sugar. Now, what is the molecular weight of glucose? 180 no I will do write that. So, molecular weight of 180. So, therefore, 18 gram C6H12O6 is equal to 0.1 mole. So, therefore, the enthalpy change for 18 gram 278.7 kJ per mole. So, this much energy is available to us, because we only took 18 gram. Okay. 18 gram is just one spoonful. Now, we are going to climb up, a 70 kg man is going to climb up with an angle of 30 degree. So, let us say climb up x distance, x meter, right. So, if it climbs up x meter, what is the height that is going to be changed? That is x sin 30 degree. So, x sin 30 degree is our h. Sin 30 is how much? Half. So, x sin 30 is this one, then mass is 70 kg and g is 9.8 meter per second square, right. So, which is x by 2 into 70 into 9.8 is equal to, or we can actually we can do that right away. So, now x by 2 into 70 into 9.8 is now equal to 278.7. So, negative I am not using, because that negative is basically giving us energy. So, that is a positive now. So, how much x we are getting? 278.7. Okay, by the way, this is kilojoule. So, we have to add this much, because this is joule, right. This is joule and this is kilojoule. Okay. Just calculate that and let me know how much you are getting. 812.5 meter, and the height, that means the height that it is climbing is half of that, almost 400 meter, and that is higher than the Eiffel Tower or the Empire State Building of New York, which is around 380. So, a sugar is that much, giving us that much energy. So, ideally it is not the thing, because of course, if you calculate the energy wise, then it is coming out to the same, but this energy is as if somebody is lifting you. So, let us say a lift is pushing you up that much, that is the energy that is going to spend. However, when we take a step or climb a stair, then in our body there are a lot of muscles, lot of other things that are working continuously. So, it is not just the gravitational work that our body is doing, our body is also doing lot of internal muscle work at a molecular level, that spends a lot of energy. Our blood pressure is going to be higher and our muscles is going to be stiffened, and many other things that are. So, therefore, ultimately actually we are going to use more calorie by climbing that much, but even then it is an important thing to understand more or less the ballpark number that we get from that. So, the amount of energy that actually is there in a very in one spoonful of sugar.